what we're doing. So we're talking about a relation R, and we are talking about another relation S. And in this case, we see that this relation consists of the members, that is this one, that, and that one. And then R and S consists of this. So now you're asked to obtain, if we were to obtain R composition S, what we shall have. Look at what I'm doing. You have one are related to two. What you're supposed to do in as far as the second relation is concerned, look for the member that has two to be the first one, and you see we have one are related to two, and in this one that two is are related to three, and therefore R composition S will be R1 R related to RS related to three. You see, so we shall have 1, 3, you can see that. And then in this second one, look for another member that starts with 2. And you notice that we have this. So we have 1 R related to 2. Here we have 2 is S related to 1. And therefore, the member of R composition S will be 1, 2. You see, look at this 1, and then 2, 2, 1. So we shall have 1, 1. And that is why we have that. We do not have any other member that starts with 2 in the second relation. So we move to the next member, which is 2 are related to 3. We would want to look for, that is, members of S that start with 3. Let's see. 3, 3, 3. No, it is not there. So that is to say that now this one cannot be, that is, transition to the second relation in a manner that we can obtain a member of R composition S. Now, when we go to this member 3, 4, all we need to do here in the second relation, look for 4, look for that 4 that starts with that member that starts with 4. And we have this one and this one, these two members of this relation S. So we shall have 3 are related to 4. We have 4 are S related to 1. So in that case, we have therefore 3, 1, and that is why we have this. Now, again, 3, 4, and then we have 4, 3. So we have 3 are related to 4, 4 S related to 3, so we shall have 3, 3. And that is exactly what we have here. Now, there is none other that starts with 4 here, and therefore we are done with that. We go to 2, 2. In 2, 2, here, this is 2 are related to 2. We would need to look for a member that starts with 2 in the second relation. And what we have in this case is this one and this one. So we shall have 2 related to 3 in the composition of R and S, and that is exactly what we have here. Here we have again 2, 2, 2, and then 2, 1, and therefore 2 is related to 1 in as far as the composition of R and S is concerned, and that is where we have that. And these ones are the members of the composition of R and S. Let's look at the other way around. We have now S composition R. S in this case starts and then followed by the relation R. We would want to see whether we shall have the same elements or not. If they are not the same, then we shall say that those two, that is, composition of relations is non-commutative. They do not commute. They are not, that is, composition of relations is non-commutative. Non-commutative, this is what we mean. Non-commutative. Now, let's see. In this case, if we start with S, then we start with the members of S. We have 2 S related to 3. We would want to look for, there is a member of R that starts with 3. It is here. So we shall have 2 S related to 3, 3 R related to 4, and therefore we shall have 2, 4. And that is why we have this. We would want to look for another member of R that starts with 3. Apparently there is none, and therefore we move to the next. 4 S related to 1. And we would want to look for the members of R that start with 1. So we have this one, there is none other. So we shall have 4 S related to 1, and then 1 R related to 2. So we shall have 4, 2, because 4 S related to 1, and then 1 are related to 2, so we shall have 4, 2, and that is exactly what we have here. Now that we don't have another one, we go to 4.3, and this member here of S, we look at the case where we have a member of R that starts with 3. We see that we have this one, and this is the only one. And therefore, 4S related to 3, and then 3 are related to 4, so we shall have 4, 4. And that is exactly what we have here. When we go to 2, the member that is of S21, we look at again, there is a member of that has 1, because now this one is 2S related to 1, and we have on 1, and therefore we shall have 2S related to 1, and then now 1 are related to 2. So we're going to have 2, 2, and that is it. Those are the members. When you compare these two, you notice that R composition R, R composition S is not equal to S composition R. As you can see, the members of these are different from the members of this. And therefore, we say, therefore, that a composition of relations is non-commutative. Well, this one's, when you have R composition R, you're going to have R squared, R composition R, that is when you compose R to itself, that is 3 times, then we shall have that, and so on. And therefore, that being the case, we see that yes, that leads us to that. And well, you need not even bother yourself so much with that. Now that we're done with composition of relations, what I would wish to take you through is what we call representation of relations. And here we are. Look at this here. We told that there are 3 ways of representing relations. The first way of representing relations is by use of a diagram, an arrow diagram. And apparently I didn't draw this here. Well, I planned, I say that I will, that is taking you through this, that is in the lecture. And here we are. We have, this is A, so we have 1, 2, 3, 4. And then we have, that is A, B, C. So what we see is that this is at A, and this one is at B. And this relation here. Let me hope she has done the necessary, right? Okay. Excuse me right there. Let me hope that you... Oh. Can you please mute? Excuse me, mute, please. Now, we have, again, this fellow is still hasn't muted yet. Let me hope. Okay. That is okay. So we have one is R related to B. So we have, there is an arrow. Let me use different ink here. Maybe let me have it. I could even have green. So we have that related to B. Look at that. One related to, that is C. Look at, oh, that is not very nice. It should be a bit straight. It should be more straight than that. We have, that is, what is it? Okay, it was a bit slow in showing. So we have that. We have that. 3 are related to B. So we have that. That is 4 are related to A. So we have that there. And then 4 related to C. So we have that. That is what you call an arrow diagram. That is it, in as far as that first one is concerned. Using a table, a relation is a table. Again, we have these two sets, of course, that is A and B, and then 1 related to B. So here you see we see that we have a dash in as far as one is not are related to A, and that is why we have a dash. Excuse me, one related to B, that is why we have that. Again, one not related to C, we have a dash. One not related to D, as we can see, we don't have that, we have a dash. Two not related to A, and you can see it's not there. Again, that is to B, not there. Two related to C are related to C, that is it. So anywhere that we don't have any relation, we represent it by a blank. Three related to A, you can see that is what we have here, and you can see that. And then these ones are blanks, all the way to three related to D, are related to D, and then four are related to A. And that is exactly what we have. So this is what we call a table. Now, as a directed graph, this is also important. Look at what we're doing. In this case, one related to itself, that is unrelated to itself. What we do, you can see this is represented by this. You can see that it is related to itself. One related to two, you can see that it is related to two. And then if these ones are called nodes, these ones are called nodes or vertices, nodes or vertices, nodes. When we talk about that is, sorry, nodes, sorry. That is that is a capital D, sorry. No, that is D, I mean, not capital, rather. Not T, node, I mean. Okay, so let me go back to my red ink. So this one's 1, 2, 3, 4, all those are called nodes, right? Or a point, or that is a vertex. At times we call it a vertex. So when you see a vertex, then that is what we mean. Now these ones are called edges. You can see like there is from 1 to 2, there is an edge. Also even this one, all those are edges. You can see this one is 1 are related to 2, you can see represented by that, and then 2 are related to 1 again. You can see that it is taking us back there. 2 are related to itself, so you can see this one is represented by that. 3 related to 2, you can see that. You look at you can see that it is directed to 2, that is 3 related to 2, and then again 3 related to 4, and then you see we have 4 are related to 3, right? That is it, and then we have 4 related to itself. So this is what we call a digraph. In fact, we either call it a directed graph or a digraph, and we're gonna see that that is when we deal with what we call graphs. So of course, each one of these is what we call, that is, it is what we call an edge. Also called an arc or a line or a branch. Yeah, all those mean the same. Again, we've looked at 3 ways of representing. We've started from an arrow diagram, a table, a directed graph or a digraph. And then let's go to what we call a relation as a matrix. And this is where we shall have what we call an adjacency matrix. You can see that. We also call it a relation matrix or a Boolean matrix. So at times you could be asked to find the adjacency matrix of a certain relation. And let me hope that you're gonna at least have an understanding of what that is. Okay, I thought maybe there are some fellows who would want to join. Aunga Walter, Walter, you are raising your hand. What is up? Oh, there seems to be nothing. Okay. Okay. Aha. Melenta Toriki. I hope you've taken care of your device. All your colleagues are okay. Okay, Mwanyagwara, share the note kindly. The PDF you're using. On the PDFs that I'm using for that was 14 minutes. That is around 16 minutes ago. Probably I was using the other one. No worry. That one I will do that. So that is okay. So let's go to this. There is a relation as a matrix. And now here, of course, to know to engage yourself, to engage you through this, I wish to say that you allocate one where there is a relationship, where the elements are related. You allocate 0 where they are not related, and that is exactly what this is telling us. For this example, for example, we have I've done this purposely. The outer part. Many times we don't indicate these ones for purposes of enabling you to see that clearly. And in this case, we see that we have A, B, C. The first element, the first set, we order the members. That is, of course, you see we have that this related to 1, whether it is the case, yes, A are related to 1, and A are related to 1, you have that is the second, that is set bearing those elements horizontally. Of course, these ones represent columns. Be very careful. You can see that these ones represent rows where we have this. We have A related to 2, A related to 1, A are related to 2, A are related to 3, A are related to 4. Just in case we have, if A is not related to 2, then you allocate 0. And that is why we see that here A related to 1, that is why we have 1. We don't have A related to 2, that is why we have 0. We don't have A related to 3, that is why we have 0. A are related to 4, yes, that is why we allocate 1. B, we don't have B are related to 1 here, so that is why we have a 0. B are related to 2, yes, that is why we have 1. B related to 3, yes, that is why we have 1. B related to 4 is not there, therefore that is why we allocate 0. C related to 1, it is there, that is 1. C related to 2, that is why we have 1. Then related to 3, C related to 3 is not there here in the relation, and that is why we have a 0. And C related to 4 is not there here, so therefore that is not a member of this relation, and that is why we allocate 0. This is important because you notice that when you're talking about adjacency matrix, there is something that is cooking bit by bit as we go along. Yes. In fact, when we go now to what we call Boolean algebra, we shall get to a point where we have we have two very important values to allocate. So we have what we call 1 and 0. So we shall get there. But even before that, you notice that when you're talking about a relation here where there is no relation, we allocate 0. Where there is a relation, we allocate 1. So I think up to there, we are good enough. And what I'd wish to do is to take to what we call an equivalence class. An equivalence class, and that comes immediately after what we call an equivalence relation. Let's see that. Yes, just let's see that. I think it must be somewhere here. Yes. We've talked about an equivalence relation earlier. We said we have what we call a reflexive, that we say that a relation is said to be an equivalence relation if it is reflexive, symmetric, and transitive. And I think you still remember this when you're talking about reflexive, just to remind you using these notes. And I am doing this deliberately, using this set of notes here, so that you see what I'm trying to do is to ensure that my students are flexible enough in terms of, you see, whatever whatever notations that they'll come across, you should be able to have an understanding that, oh yes, you see, this is the same notation as what we did in class, so it should not again at times maybe make you wonder whether we are having new notations or this could be meaning something different. And that I felt that it is important to expose my students further so that at least you know all the acceptable notation for some certain concept. And that is exactly what I'm doing. And just like what I mentioned, like those ones, you can see we're using these types of you see enclosure, apart from, of course, using these ones that I mentioned earlier in this lecture. So this one is an adjacency matrix, and you can see the same thing. You can see one is related to A. Of course, we have that is A, B here, A, B. We have here that is 1, 2, 3. So 1 is related to A, 1 is related to B. Let's see, 2 is related to A, but there is no 2 related to B. That is why we have a 0. 3 related to A. Again, these ones are adjacent matrices, but that is not where I was heading to. What I was trying to take you through is, again, you see, to remind you about what you call reflexive, you see, reflexive, transitive, you see, and then symmetric. Yeah. So it is the same, you see. Like in this case, when you're talking about that is, remember, I'm taking you to what to call that is an equivalence relation. You're told that a relation is said to be equivalent if it is reflexive, symmetric, and transitive. So in the case of a reflexive, we know that as an element is related to itself, you still remember. You see, that is something that you should remember. If anything, there is an error here. This one should be X is related to X. Yeah, X is related to X, right? That is what we mean by reflexive. When we're talking about that is symmetric, when X is related to X, Y, again, Y is unrelated. You see, we have some kind of it's as if we're having some kind of commuting that X is related to Y. If that is the case, imply that Y is related to X. And as you can see, what I mentioned earlier is that relations are not commutative. I think I mentioned that. I say that it is not the case that when, even the case of composition of relations, they are not commutative, even without composition. Also, you find that not all relations are, you see, we do not have that commutativity property. And that case of commutativity property, in fact, you notice that this case of symmetry is to some great extent so close to that, you see. 23 minutes to somebody who wants to join. Interesting. Anyway, it's okay. 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 So we have that symmetric, and then we go to transitivity. So the case of transitive, you see if X is related to Y and Y is related to Z, then X is related to Z. And again, you notice that you must be very careful not to confuse this with that is what we call composition. You see, yeah, because again, you notice that there is something similar to that. You see, X related to Y and Y is related to Z, but we're talking about one and the same relation here. But when you're talking about the composition of two relations, you see, I'm pointing out this so that you have a distinct or rather a clear difference between transitivity and so that you don't confuse with what we call, you see, what we call composition of relations. Here we're talking about a relation and another one and the same relation. But now when we're talking about composition of relations, you notice that if this is in, let's say, in relation R, and this one is in a relation S, then X, you see, there is XZ is in relation R composition S. You see, that is it. So if we have these three properties, then that is when we say that there is a relation is an equivalence relation, you know. And we've done that. We even did that last time. So now, when do we say that it is a reflexive? Of course, this does not relate to what you call an equivalence relation. I just felt that I should take you this. When do we say that a certain relation is a reflexive? It is just like the other case when last time we talked about asymmetric and antisymmetric. There is a difference between asymmetric, there is an asymmetric, and an antisymmetric. You see? So the same case here, when we're talking about reflexive, a relation is said to be reflexive if for every member of, you see, we're talking about, it is important that we talk about this here. Let me take you back. You see, it's good. Seeing is believing. Look at this here. Or reflexivity tells us for every member of X, you notice that X is related to itself. So that if we have, let's say X to be having, let's say to be a set of the elements 1, 2, of course, X cross X here, you see, consists of all the members of X cross. You see ordered pairs. You see, look at this here: 1, 1, 1, 2, and then 2, 1, and then 2, 2. This is what to call, in fact, this one is what to call, if you remember, this is what to call a universal relation. 1, 1, 1, 2, 2, 1, 2, 2. This one is 2, 2. This one is 2, 2. This one is 2, 2, 2. Now, we say that a relation is reflexive. Let me give you an example of a reflexive relation from this. This relation, let's say 1, 1, maybe 1, 2, 2, 2, is reflexive. Why? For every member of X, we have every member related to itself. You see, 1 is related to 1, 2 is related. That is what we mean by reflexive. Now, what do you mean by anti-reflexive? Look at this. If for every, you see, if for every X, every member of X, no member is related to itself, this is an example of anti-reflexive relation. Look at this. Let me give you an example here. Of course, from this, that is, if X is equal to consists of those elements. An example of anti-reflexive relation is this. That is an anti-reflexive relation because there is no element that is related to itself here. And I think you can see this is an example of an anti-reflexive relation. But if, suppose we have, let's say, as this relation, we have 1, 2, and then we have 1, 1, and then we have 2, 1. Of course, in using the curly brackets. This one is not an anti-reflexive relation because there is an element that is related to itself. So it is not irreflexive. It is not irreflexive. For the condition for reflexive, there is no single element that is related to itself. And for the case of reflexive, every member of X is related to itself. So this one is neither reflexive nor irreflexive. Are you seeing that? This one here is not, it is neither. You can see this one. This one is neither reflexive nor irreflexive. It doesn't meet the threshold for every definition here. Right? Anti-symmetric, we did that. So that is in as far as this case of, you see, we are talking about equivalence relation. So that is clear now in as far as equivalence relation is concerned. What I want you to have is, okay, look at this. We have what you call, that is okay, an equivalence relation is okay. Now, there is something else here that I would want to take you through this evening, what you call equivalence classes. And I'd want us to go through slowly, bit by bit, all the way to the end, and get to know exactly what we mean by equivalence classes. The first condition is that the relation must be an equivalence relation. And as we know, an equivalence relation is a relation that is reflexive, symmetric, and transitive. That is what we've been told here. That the condition is for an equivalence class to be obtained, then, and remember these equivalence classes are generated by members of X, by member of X or by members of X. First condition is that R must be an equivalence relation. And we told that for any member of X, any X, this the set, look at this, what is inside this? It is that small x, that member of X. And meaning therefore, and it is important to know this, that this equivalence class is just a member of, it is a subset of X, not a member, but a subset of X. So it means an equivalence class is not a subset of the relation. It is a subset of X. This set X. Remember, R is obtained by relating members of X. And if we relate members of X, of course, we know very well that R is a subset of X cross X, because we see that we relate members of X to members of X, and that is how, of course, there is a way this R does so that it relates those members of X to X. So this one is a subset of X cross X. But an equivalence class is a subset of the set X itself. And how do we get this? Look at this. It is equal to the members Y such that X is related to Y. For Y, of course, again, members, that is for some Y that are found in X. So all these Ys, these members of this class are simply, that is, members of X that are, you see, that are related, that remember here, that X, that R relates X to. Let's be careful there. We don't say that it's Y related to X, because then that is to say that we're starting with Y followed by. No, we're saying in this case that an equivalence class, you see, what is binding here is that relation. Remember, this R is an equivalence relation. It means it is reflexive, symmetric, and transitive. And that the members of the class are those members of X that R relates X to. It's important you digest that. And this class is called also R equivalence class, generated by X, generated by members of X, you see. In fact, not a member, by one member of X, you see. Now, if that is the case, then let's see. Therefore, an equivalence class is the set of all elements which are related to X by an equivalence relation R on X. Yes. There is a term I wish to take you through here, and this is a term that will come in handy in a number of instances. Not only in this case, but it will be there in a number of cases. And they are generated, in fact, from the set of all integers. And that is why you remember last time I took you through the set of integers. The set of integers, of course, consists of all whole numbers, both negatives and positives, including a zero. And if we may use, that is the number line briefly, we see this one 0, to the left is 1, to the right 3, and that continues. Remember that is infinite. We have -2, that this continues also infinitely. So what happens in this case is that we have -2, -3. All these are integers. You see? And if you remember, either written by that or this one, if you come across that, that is the set of integers, you see that we just use dotted lines to represent, of course, the infinite nature in which those ones negative integers flow. And then we shall have 0, 1. Then that continues 3. And then, of course, we use again dots to the right. This is the set of integers, right? Let me hope that you still remember that. Now, for us to have a better understanding of, you see, what we mean by equivalence classes, let's look at what is happening here. Now, we have this example that takes us through the set of integers. And our R is the relation congruence modulo 4. What do you mean by congruence modulo 4? We say that X is congruent to, in fact, we write it this way, it is here. X is congruent to Y modulo 4 if the difference between this and this is divisible by 4. Please have a grasp of this because we shall use it somewhere else. We say that X is congruent to Y, written this way. This one is congruent. This symbol here that looks like an equal sign but has 3 horizontal lines. If X is congruent to Y modulo 4, if X minus Y is a multiple of 4, or it is divisible by 4. So you notice the members, look at this here carefully. You see the set of integers here, right? We see that we have this relation, congruence modulo 4. And remember, this relation, congruence modulo 4, is on the set of integers. We're simply talking about those integers. When you obtain their difference, all of them are divisible by 4. Right? So if we pick, let's say, 0 here, what do you mean? This is an integer, this one is an integer, this one is an integer, this one is an integer. And therefore, in agreement with what we said here, you see our X in this case is the set of integers. Here now we have 0, 1, 2, 3, and so on. We could even have -1, -2, -3. You see? Now, what we want to see here is that, you see, this X is the X that we're talking about here. So 0 minus -4 should be divisible by 4. And it is true. So you notice that you see X is congruent to -8 mod 4. Because when you say 0 minus -8, it will give you 8 divided by 4, which is true. It is divisible by that. 0 minus -4 is positive 4. The same case here. You notice that the members of this class, this equivalence class, is that you notice that 1 minus -7 is 8, which is divisible by 4. 1 minus 1 is 0. 0 divided by 4 is 0. This is divisible by 4. 1 minus 5 is -4 divided by 4, that is -1. 1 minus 9 is -8, which is divided by 4, which is divisible by 4. So all these are what you call equivalence classes. And you'll notice that these ones will not stop there. These will continue, right? But now there is something. They'll continue up to where? It is important to note something, that when we get to 4, the equivalence class, you see we have this, we have 4 here. When you look at this carefully, which are these integers that are in this class? If you're very careful, you'll notice that this one is the same as this. Because then, which numbers can you subtract from 4 and you get those numbers to be divisible by 4? The first one, in fact, the one that is obvious, even if you want to consider the positives, it is 4. Start even from 4. No, in fact, even 0. 4 minus 0 is 4 divided by 4 is, you see. And then the next one is 4. 4 minus 4 is 0. Divided by 4, yes. The next one is 8. 4 minus 8 is -4. To the left is -4. 4 minus -4 is 8, which is divisible by. The next one is -8. And of course, this continue to the left, you see. So we shall have to the left, we have some dots to the left, and we have some dots to the right. And when you look at this, it is no different from exactly what you have here. So you notice that these concurrence classes. Now, how about -1? Even if you want to have -1. If you are keen, -1 then this class with this class -1, and of course we have R here, this class here, if you are very careful, look at that. Which integers can we subtract from -1 to have, I don't know whether you're seeing that, to have a number that is divisible by 4? It is, one of them is -5. -1 minus -5 is equal to, it is equal to 4. Divide by 4, yes. So where is -5? You can see this one is the same as this class. This one is the same as this class, even if you want to go to negatives, because then those are members also of the set of integers. So you notice that the only unique classes that we're going to have will only be this. You see, that is why I started. I say that you may go on, but again, even if you go on, you're going to find the same. This one will be no different from this one here with 4 here, will be no different from this. And therefore, to get you back to that, right? That is it. And that is what we do. You can see now. We have only these 4 classes in as far as. And there is a section that I will relate you to this. I'll take you to this. I'll bring you back to this later, right? I'll bring you back to this case of congruence modulo n. Oh, I can see that we have 3 minutes, and I think we can't go beyond that. So, well, we shall meet in our next lecture, which is on Monday, our physical lecture, to continue from where we left. And I want to believe that we're going to do very well. Please, as to the case of revising, I think there's something that I mentioned last time. I said, always ensure that you familiarize yourself with the stuff that we do every lecture. Okay, Mo, take your cool. You are not relaxed. Be relaxed. Be relaxed. Be relaxed. You're going to have the no, so don't.